Okay, first of all, of course, thank you for the opportunity to talk to this audience. My talk will be kind of correlated with the talk of Salvatore in the sense that I'm working as a mathematician in the domain of splines, and I used together with Salvatore splines to get a fitting model to invert the Laplace transform. So, but my talk is only about splines, model for data representations, and it will be very basic. I just want to give you the idea what is in the back of splines. So this is the main question. What is a spline and how can we use it to model a set of discrete data? First of all, it's important to know that spline means two different things. The first one is that a physical tool that was used in the past by shipbuilders to draw ship profiles. And it is also, and this is more important for me, a piecewise defined function with a certain regularity. And here you see what I mean as a tool is indeed this thin stripe of wood that you see in the picture that was used by shipbuilding builder to draw the profile of a ship. And you see some black stuff that are weights, or they were called actually ducks or knots that were used to put the stripe in a given shape, okay? And the important is that the influence of each of these weight is great in the vicinity of the point where the weight is attached, and decreases going away from the weight, okay? And this is essentially the locality of the spline. And mathematically is a piecewise defined function with a prescribed regularity at the conjunction. So here you see in this picture, for example, on the right, we have a Bezier curve. I don't know if you have ever heard about it, that are special instances of splines, polynomial splines, and on the right, one possible piecewise defined function. They are important and find application in several domains. Here I just mention as an example animation, computer animation. So some, for example, this character at Pixar, in a Pixar cartoon is modeled by splines. Or of course, we can model the trend of data like the one we have seen in the last 2 years concerning COVID, but we can use splines in architecture, design, art, automotive. So they really are very much used, in particular in geometric modeling, everything connected with geometric modeling. The spline, they were, as a mathematical tool, they were introduced by Schoenberg, a Romanian American mathematician, and in the 60s worked a lot on the subject, providing very important mathematical results. And he was working with them for quadrature rule, for cardinal interpolations, many different type of applications. But then a great impulse to the spline domain was given by Larry Schumacher and Kat DeBoer. They are still alive and still active in the domain. And they both wrote two crucial books. One is more theoretical and the other is a practical guide to spline that I would recommend you to read in case you want to use splines. If you search on, say, for example, Scopus, and the word spline in a title, you get 62,000 papers. So it's really a rich domain of research. And every year you can read there is an increase of number of publications. Certainly, this is also due to the fact that there is a large variety of spline. People working in spline call the set of spline the zoo of splines. You can have polynomial splines, exponential splines, rational, subdivision splines, Chebyshev splines. And according to the type of spline you use, you have different type of applications, including image analysis, solution of partial differential equations. So they are actually, for example, used in also in finite element methods for the solution of partial differential equations. So according to the type of spline, we have a different type of application. My interest in spline is threefold. So first of all, you can interpolate exact data with splines, like was mentioned by Salvatore, or you can smooth noisy data, and this can be important in case you deal with noisy data, or you just try to follow the trend suggested by the data. And we, in this case, we call the spline model just an approximant. But recently, they also are considered as state-of-the-art for technique that infer knowledge from data. For example, they are used as activation functions in deep learning, or they are used to predict data behavior in data analysis. To be a little bit more precise, I will describe you more in detail how we can construct and define a spline space in the simplest situation, which is the univariate case, and polynomial. So, as I said, there are many types of spline, and I will focus on polynomial splines. So the idea is that we are given with an interval, because I'm considering univariate splines, and some knots inside the intervals, say Xi1, Xm, and a degree, spline degree, which is P in my slide. And the spline is a piecewise polynomial. So you see it's a polynomial when restricted to each subinterval with a certain degree of regularity, which is prescribed by the degree. So if P is the degree, the regularity is at least P minus 1 at each internal knot. And then here you can see an example. We have a linear spline here, which consists of line segments that are connected C0 because the degree is 1. And here we have a quadratic spline. We have two arcs of parabola that are connected C1 because 2 is the degree. Certainly the most common splines, and I have to say that sometimes people confuse the two domain because the more common is a cubic spline, but spline is a more general concept. Cubic spline is made of cubic arcs that are connected C2 smoothly. And the picture, is there any pointer here? No. No. Okay, so this is the cubic spline. So we have 3 arc of cubic parabola that are connected C2. And here on the left, you see, for example, arc of parabola that are connected only C1, and here only C0, and here also a situation where we have discontinuity. And all these 4 pictures represent splines, essentially, in a general sense, but only the last, this one is a classical cubic spline, where we have C2 regularity. Okay, of course, if we want to do something with spline, and we want, for example, to construct an approximant, a given set of data, we need to identify the dimension of the linear space, the span. And this is simple in this case to do, is in general not that simple, in particular in the multi or bivariate setting. And here is simple because we know that we have m-1 subintervals. In each interval, we have a polynomial of degree p. So altogether, we have m-1 times p plus 1 conditions. And we have to consider continuity, so we have to subtract the continuity condition at the internal nodes, and therefore it's simple to compute the dimension of the spline space, which is M plus P minus 1 if M are the knots and P is the degree. So there is a strong link between the dimension of the space, the number of knots, and the degree of the spline. Okay, and of course, to know the dimension of the space is crucial, because if you want to write a spline, we need to have a basis for the spline space. And in this case, it's simple, as I said. In other situation can be more complicated, because we can allow spline to have different knots multiplicity, or different degree of segments, or different type of segments. Okay, and but once we know the dimension of the space, what we need is a basis for the space to write any function in the space. And what is important and crucial is that spline, for example, here I'm talking about polynomial splines, they possess an optimal basis, in the sense that is not only a set of linear independent functions that span the space, but they also satisfy this four nice property, very crucial in applications. They are bell-shaped, non-negative, compactly supported, and form a partition of unity. All those conditions implies important property of the spline. And the basis that satisfies these properties is called a B-spline basis. This B stands for basis, bell-shaped, and someone also suggests the name of Debord, that is the father of B-splines. Okay, so once we have a basis, we can construct a spline model to approximate a given set of data. And the simplest way is certainly to construct a least square polynomial splines that approximate the data. So we are given with a set of data, say xi, yi. We can assume they are noisy. And the spline that is that we search is the one that is written in terms of the basis, of course, and whose coefficient are the solution of this minimization problem. And once we have the coefficients, the spline is also called sometimes a regression spline. Okay, the problem with this approach is that we need knots to define the basis. And in particular, we need to decide how many knots we want to include in the spline space, and the location of the knots. And these are not given with the data. So it's something that needs to be fixed by the user. And this is certainly complicated. In particular, for example, if we take too many knots, like we let the knots coincide with the ashista of the data, the problem is that we get overfitting, because the solution will be the interpolant the data. Otherwise, we can get underfitting, for example. But of course, for us, the best would be to get a model which is a balance between overfitting and underfitting. So another solution is to consider a smoothing spline. Maybe some of you happen to use smoothing splines. Here, the philosophy is a little bit different, because we do not only minimize the error or the loss function, sometimes it's called the loss function, but we include the penalty term, which is here in the spline context. Classically, the penalty is this, say, integral of the p minus 1 derivative of the spline. And of course, we write the spline again as a combination of B splines. And in general, I mean, can be shown that the solution, the minimal, is reached when the knots of the spline coincide with the ashista of the data. So we do not have any problem in selecting the knots. They are essentially given by the data. But here the problem is to select the smoothing parameter, because is not given by the data, and it affect the fidelity or variability with respect to the data. And we can see a great difference if we choose one lambda or another lambda. In particular, If lambda is 0, we are back to the overfitting problem because we get the interpolant. And if it's too big, we get underfitting. So it must be chosen in a clever way. And people studied the way to choose it. For example, I mentioned the cross-validation method or L-curve method. There are methods, and they are mainly proposed by statisticians. So, but there are other alternatives. For example, we can use penalized splines, so solve a penalization problem with a penalty term which is simpler with respect to the classical penalty term of smoothing spline. Here I decided to talk about P-splines. This P stands for penalty and polynomial. And they were proposed by two statisticians, Euler and Max, 25 years ago. And the key ingredients are cubic spline and B-splines based on uniform knots, so that the problem of selecting the knots is not boring. And then other particular property of B-spline that are well known and will enter into the game. And then, of course, a certain level of approximation. So the P-spline is the solution of a penalty minimization problem, penalized minimization problem. So here we are given with a set of data points. We decide to work with cubic spline. So P here is no longer doesn't exist because P is 3, is fixed. And then we write the spline as a linear combination of cubic splines, and we get the coefficients by solving the coefficients of the expansion, by solving this minimum problem. And you see here, there's no longer integral of the derivative of the function, so is a penalty term which is much simpler, and it involves differences, second order differences of the coefficients. So if we solve this problem, we get a smoother or a regression spline, which is a good compromise between the smoothing spline and the regression spline. They have a very nice property, like, for example, they fit the constant and the linear polynomial data exactly. So if it happens that your data lie on a line, you get the same line back. They conserve the moments of the data, which is also important, and they do not show boundary effect. The boundary effect were mentioned before by Salvatore. If you have a model that does not behave well at the boundary of your domain, it will affect, for example, the Laplace transform inversion. Of course, the limit of this type of spline that I talked about so far is that they are based on local polynomials, but your data can show a different behavior. For example, they can show an exponential trend. And then maybe to work with locally with polynomial is not the best choice. And this is the case. For example, if you have data like that, you have your data, the y is a perturbation of a function, sum of exponentials, evaluated some ascissa. Then what can you do, and which is the best spline type to use to approximate this type of data? The idea is to replace polynomial spline with exponential polynomial splines, and then, of course, to construct an optimal basis, which is made of exponential polynomial B-splines, and then generalize the idea of P-splines. And this is what we have done. This is a recent work I've done. And the idea is to construct a spline with the segments in this space. Okay, so we leave the domain of cubic polynomial, and we work with exponentials and polynomial times exponentials. And still, I mean, we decided to work with the 4-dimensional space to mimic the cubic splines. And then, of course, we first had to construct the basis for this spline space. And we wanted to have a good basis or optimal basis. So we construct a basis that satisfied all the nice property I showed you before. Bell-shaped, compactly supported, regular, and reproducing certain spaces. And then we solved a penalized problem with this type of splines. And we worked on this minimum problem, but decided, as done by Euler and Max, to simplify the penalty term. And so working on these spline properties, but here there are some technicalities that I will skip, we end up with a minimum, with a structure which is very similar to the one I showed you before, but now both the basis and the penalty term will involve the frequency that we decide to use. So the alpha that identify the spline space. And so this is our proposal. And I like to observe that whenever alpha, so if we select a frequency which is 0, we are back to classical cubic splines. And so our HP spline become P splines. So in this sense, it's a real generalization. And then from a practical point of view, the problem is this, that we have to solve is a linear system, the solution of a linear system. Here I wrote the system to let you see that the matrix that is defining the linear system is depending on B and D, and is therefore a matrix with a localized structure, which is good from a numerical point of view. And the say condition number is not too bad. And then what we get is that our model is capable of reproducing not the, say, lines, or so polynomial degree 0 and 1, but exponential functions. Here is an example just to show you that if I take data, I don't know if you see the data are in red, in red. Sorry, these are exact in this case, of course. And I draw my HP spline, I get exactly the function from which the data comes from. And this is not the case with P spline, because they are based on polynomials, not on exponentials. And similar for the moments, we do not reproduce the moments, but we reproduce something which is connected through exponentials. And then you can see here a couple, I show you a couple of pictures. The first example is the application of this smooth, say with this smoother, yeah, we can call it a smoother, to a real data set. And the second concern a set of data points that are synthetic. So we constructed evaluating them, evaluating a exponential function. And this is, you see, from the left, you see the data. And the two functions that are drawn are, one is a polynomial spline, the other one is exponential polynomial spline. Here we don't see much of a difference. And this is what we expected, because there are no prior information about the behavior of the data. So it's okay, we were satisfied. But when we take a function like, for example, this, which is a combination of positive and negative exponentials, and we construct our approximant, we see that our approximant better follow the trend of the data. In black is our approximant, and in magenta is the classical polynomial penalized spline. And this is true for different level of noise and for different selection of the smoothing parameter, and also for different selection of number of nodes that are still free parameter. Okay, so I just want to conclude. I wanted to show you that spline are simple but powerful tool that can be used to approximate the data. The important is that according to the type of application, we can choose different type of spline, and this we should keep in mind. In particular, I think that this class of penalized spline offer many possibilities, and you do not have the problem of selecting the knots. You do not end up to get overfitting or boundary effects, and also you have moments, exponential moment preservation, which is important. The only drawback, some sense or problem, open problem, is how, given a set of data, you select both the smoothing parameter and the frequency parameter. But there are actually, for the smoothing parameter, I already told you that there are classical methods. For the frequency parameter, we are proposing now some numerical method based on linear algebra that allow to get a very good selection of alpha. And that's all I wanted to tell you. Thank you very much. I hope it was not too noisy.
Thank you very much. Questions for Costanza?
Thanks, Costanza and Salvatore for the talks. And okay, just practical question, also related to this spline interpolation and extrapolation, I suppose, because when we work with our NRQCD data that our data that Chris was talking about before, so we have this issue that we have on a limited interval in a space, direct space that we want to invert back. But then it makes a crucial difference for us whether an exponential is a good asymptotic behavior of this data, or rather this data turns into a power law type of decay. That's important change in the data that we need to detect. And I mean, can we see anything like that by working with splines? I mean, or in other words, can we realize when an exponential decay is fake, maybe it's a good approximation for the data, but is there any symptom that tells us which extrapolation?
I mean, in a way, everything can be solved by identifying the correct frequency, okay? That is the best indication of an exponential trend in your data. And so you indeed, we really need a good identification of alpha. And of course, we could extend the spline space, but the moment we didn't consider this case and consider more frequencies, for example. So if you have alpha 1, alpha 2, and then maybe you get a spline with the component in one of the two frequencies more relevant than the other. So maybe we can solve it. We could solve your problem by allowing a richer spline space with more frequencies than only one. Can we give you our data? We can try, exactly. Okay. For the moment, my model only uses one alpha. So I have a strategy to identify one alpha. Okay. And then to use this alpha to approximate your data. But we can check. Okay. Let's see. Let's see what happens. Reasonable. What? Thank you. You are very angry for data. You are very angry for data. Angry.
Well, first of all, we can give you data. Let's start with this. We can give you a lot of data. If, they need to be fitted, so we can talk about this. I'm curious about one properties of this spline. You have shown very clearly that
I'm curious about, sorry.
One properties of this spline. I mean, very often we have the need of imposing some smoothness condition on the underlying function that is higher than fixing an order of polynomial C3, C4, C5. Is there a way to compare the order of polynomial that we want to fit within the given error I mean, do we have some sort of noise measuring technique that can balance the order of the polynomial with the noise that comes from the data?
So I try to so you want to know if you can select the degree of the polynomial according to the
Noise of the data, for example.
To be honest, I don't know. I never thought and I never read something in this respect. To select the degree with respect to the noise.
Imagine that you want to recreate multiple moments. You want to seek for your model to rematch the moments of your data, as long as there is a non-noisy source, or you can distinguish these moments of your data.
I think it's an interesting approach, but I never thought about it, and I don't know. Actually, from a practical point of view, the degree of the spline is always low. We never use, because the idea of the powerful of spline is to keep the degree low, and in case to increase the number of intervals, rather than the degree of the polynomials or the exponential spaces. So maybe there exists something that connects the number of nodes to the noise. This is possible, more than the degree, I think.
Thank you very much.
Other questions, maybe from remote participants? Okay, so I don't see other questions. So thanks a lot
Thank
to all the
you.
speakers.
Thank you.